This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
And for some reason you cannot have PhD exclusive subjects, so it's open to you. It's advanced, right? You have to do a bit of more work. There is some expectation associated with it. I think that's very important to know as well, right? So it would be at a higher level than the subjects that you've done in your master's. It's important to be aware of that. Anyways, okay, cool. So we are still missing 50% of people who enrolled. All right. Again, if I don't get everyone agreeing to do a project, and it comes with the added condition that we have to do extra lectures during the first 4 weeks the next 4 weeks. So maybe 2 of these blocks of 3s, ideally 3 classes per week would be perfect, but even 2 classes per week would work as well. So under that condition, we can do a project, and if everyone agrees to do the project. Or in terms of Mark, he doesn't quite like the idea, but he's not strongly opposing it. So.
I don't know if the project is really challenging or...
I don't know, have you checked the elements? Did you see my email yesterday? Okay. Did you check the folder I uploaded?
The MS, sorry.
Yeah, on LMS, yeah, sure. But that's I uploaded information on LMS about the potential, possible project ideas. Go and check, come back to me. Sorry, I don't know your name.
Sorry, I haven't enrolled.
Oh,
I want to enroll.
Anyway, what's your name?
My name is Yuxin.
Yuxin?
Yeah.
Okay, good.
So what's a possible arrangement for that extra?
Then we can talk about it. We can agree on time that you guys are free. But we have to have a hard limit as well, because I have to modify things and you have to plan it. Really, if I don't get everyone's agreement by Friday, we continue as it is, and it will be an exam. It will be an exam at the end of the semester, plus 4 homeworks that you're going to do throughout the semester. I've already uploaded the homeworks for everything that you're going to see. Your first homework is due in 2 weeks. Okay, so that's it. Now, the future homeworks, you can start working on them if you are keen. I might add questions to it, but I will not remove any questions. So if you start working on them early on, you're not going to lose anything. Anyway, so you will have your first homework due in 1 week. How many of you checked out the resources on LMS? Okay, did you, for example, those of you who weren't comfortable with the idea of mathematical proofs, did you check the documents I've uploaded? Yes? No? Okay. There is a reason I've uploaded those things, because some of you haven't seen the sort of language that I might use in the lectures. Sometimes I rely on some prior knowledge on logic and being able to construct literally logical statements. Okay? So if you have forgotten, if you've never passed some introductory subject on that familiarize you with the idea of a mathematical proof, go and check those resources. How many of you went and consulted a linear algebra book? Okay, good. One. So all of you is on top of everything, right? I would be very suspicious of that feeling. I wouldn't believe it, because I forget things. I have to go and read stuff every now and then. Go back and refresh your memory. Hopefully, if you check out the homework, it might trigger something, so you need to go and read. About the homework again, I'm very lax about, you can't find the solution to all the questions online. You can. But that's a mistake, if you ask me, if you go and look at it. Because you won't learn it, then you will have a big problem at the end of the semester. Okay? But try to work the problems on your own. I even didn't know that you can find them online. Last year someone told me, oh, but these solutions are here. Oh, okay, good. Because I use the textbooks questions, most of them. Sometimes I add other things, but mainly it's out of the text. All right. So today we are going to... is it too bright? Should I dim the light? Better? Good. Anyways. So I'm going to talk about line search method. First, we're going to be introduced to the general ideas, what they are. Then we will see an important component of these methods, which we call step length. And we will investigate under what conditions these methods work. Then we talk about the convergence of line search methods, what it means, when they really work, under what conditions, and when we say they work, what do we mean? Then we step one step further, we talk about the family of algorithms which belong to, they are related to Newton's method. But to be able to do that, first we have to understand how Newton's method works. Some of you might have seen Newton-Raphson's method, same thing in a different context. And we try to understand its behavior. And then we talk about quasi-Newton methods, which are the methods that are similar. They're kind of like Newton's method. Okay, by the end of this lecture today, you should be able to identify a general line search method, Newton's method, and quasi-Newton methods. Hopefully you will understand the importance of step length and the associated conditions. Their name is Wolf conditions. And we will see that these conditions always can be satisfied for a generic problem, so they are not particularly restrictive. And then we will talk about different convergence properties of all these methods based on sort of definition that we saw in the first lecture. So we talk about convergence rates, etc., etc. I will show you some numerical examples in the class as well, just to get some feeling about these sort of behaviors. All right. What did we see last time? We concluded the lecture by introducing three conditions. One was a necessary condition, first order necessary condition. The second one was the second order necessary condition. And the third one was something that we call the sufficient condition. Just to see, can you tell me the difference between a necessary condition and a sufficient condition?
Our necessary condition is if you know the minimum of the fx, you will get these conditions. And for sufficient,
You made a statement in contraposition. I'm trying to. You said if you are not a minimum, you will not satisfy these conditions. You said it correctly. You used, I don't know if you meant it, but this is equivalent to, can someone tell me what is equivalent in terms of two logical statements, in terms of their not?
Not Q, not.
Exactly. So that's what you said. I don't know if you meant it. You were right, but in this weird setup. Anyways, my question was about general difference between necessary conditions and sufficient conditions. If we say something has a property, for something to have a property, it is necessary for it to have another property. It means if the second property is not true for what we are discussing, the first property will not definitely be true. Okay? But it doesn't mean that if it holds the first property, it will definitely have the second property as well. Okay? So that's a necessary condition. Sufficient condition is the other way around. If something has a property, definitely it will have second property, but if it doesn't have that first property, it doesn't mean it doesn't have the second property. Okay? So now, we had these conditions. So if x star is an extremum, so it can be minimum or maximum, as I said, I will exclusively talk about minima because maxima and minima are equivalent. I put a negative sign behind it. So if x star is a minimum, definitely, and under the assumption that f is differentiable, definitely the gradient vanishes at that point. Okay? Now, if x star is a minimum, the gradient, and the function is twice differentiable, the gradient vanishes, and the Hessian is positive semi-definite. Okay? So now, if I find an x star that satisfies these two conditions, it doesn't mean it's a minimum. It's a necessary condition. However, we have this sufficient condition. Now, if I find an x star that at which the gradient vanishes, and the Hessian is strictly positive definite, then it's definitely a minimum. Okay? Again, if a point doesn't satisfy these two conditions, it does not mean, I mean, mainly the second or the first one is necessary. It does not mean that it's not a minimum. Okay. Now, how can I use, if I'm going to design a method to solve an optimization problem, how can I use these conditions? What is the point of these conditions?
I think it's useful to solve the higher order functions to see it's a global or local minima.
No, it doesn't have. Here, everything I'm talking about local stuff. I don't care about global optimization at all. My question is, if I'm going to design a method, because our goal is to design a method that solves an optimization problem, right? How can I use these conditions? Because otherwise, a valid question is, what is the point of saying these conditions? Yes.
So that it's a termination.
Oh yeah, okay, good.
Sorry.
Yeek suggested that it helps to come up with a termination condition. We saw a bit of it last time, because we said if you put an iterative method, you have to stop it at some stage. Yeek is suggesting we let it run until we kind of satisfy these conditions. Because numerically we can never exactly satisfy them. For example, the magnitude of gradient is small. Yeah, it's good. It's a good way of thinking about it, but it's not the whole story. What Yeek suggested is a consequence of what we really try to do. Whatever method we try to construct, and it really applies to a massive range of optimization algorithms, they try to find the solutions to equation grad of fx equal to 0. Iterative methods to solve it. Now, then they use these as termination conditions. So many of the existing optimization methods, in the end of the day, they try to come up with a scheme that ends up whose fixed point is the solution to this equation or this system of equation and inequality condition. Were you here last week?
Sorry?
Were you here last week?
Here.
Oh, okay. No, I can't remember your name.
Ethan.
Oh, yes. Sorry. All right. So now that's the idea. Whatever we do, we try to find that solution. So we are going to consider an unconstrained problem. The aim is to minimize some cost. Decision variable, no, I don't want to. Decision variable x. And we are going to look into a family of algorithms called line search algorithms. The giveaway was the title of the lecture. And they look like that. They look like this. At any given time k, so this is, I will mainly use subscripts to represent time in some iteration. Sometimes I overload it to mean other things, but yeah, mainly throughout this subject I use subscript to represent time. So if xk is my guess at time k, I want to use that in addition to a bunch of other stuff to come up with my guess at time k plus 1, right? The way that we construct that guess is we pick some vector pk. Everything is in Rn. And then we pick something else called, here we represent it by alpha k, call it step length, step size, whatever you want to call it. So we pick a direction, we travel along that direction by some amount, that's the size of the step, and then we come up with the next guess. So that's the underlying idea. I'm here at time k, xk, that's my guess. Some oracle gives me information about some direction that makes sense. Again, we are using the language of that oracle that we introduced last time. Maybe that the oracle gives me the value of the gradient at where I am. I construct the direction, then I decide how far I'm going to travel along that direction. I travel there. It's my next guess now. I ask the oracle about something, and now I keep repeating this idea over and over and over. So in general, that's the line search method. Now we want to see what properties pk and alpha k should have so that we end up getting a reasonable result. Okay? Now we need a bit of more definition. The idea of a descent direction. We call pk a descent direction if this inequality holds. So P transpose, pk transpose, the value of P at time k, transpose the value of gradient at time at point xk. Now, to simplify the notation, whenever I have f of xk, I'm going to represent it by f of fk, because I don't want to keep writing f of xk. Laziness plays an important role in what I do. Okay? Now, we call P a descent direction if it satisfies this inequality. What does it mean? What does that equal? First, forget about this context. Let's step back. Maybe high school, maybe first year uni. If you see, if I'm given two vectors, A and B, let's look at it. What can I deduce from that inequality? A transpose B being positive. What can I deduce?
Less than 90 degrees apart.
Yeah, okay, good. But that's a bit in Rn, the angle definition requires a bit of more work. In 2D, it's the easiest way to see it. If I'm going to draw them on a plane, it means if this is A, B somewhere sits somewhere in this direction. It can be B can be there, it can be there, it can be there, etc., etc. Right? Now, what happens if I have another vector C, and C is here? What happens to that sign? Sorry? It becomes negative. So it means it's in the other direction. Very vaguely, very hand-waving way, that's what it means. If that's A transpose B is positive, it means they are vaguely in the same direction. If it's negative, it means they are vaguely in different directions. Now, what is another name for A transpose B? Inner product of A and B. Okay? How can I write it in terms of Euclidean norms of A and B if I'm defining my inner product using Euclidean norms?
Inner product, the number.
Yeah, I mean, how can I write it in terms of norms of A and B? Yeah. Norm of A times norm of B cosine of some angle between them, theta. Now, again, that angle. So if I have two vectors, I put a plane that goes through these two vectors. There is an angle on that plane, etc. But that's really that cosine. So when it's positive, it means that cosine is positive because the two terms norms are positive. Why is that? Why can't I just say the norms are positive? Okay, all of you that didn't need to look up your linear algebra books, why can I say, and what are the properties of a norm? Now, you looked at your linear algebra books, so it's good. The first property, it should be non-negative. It should be only 0 when the argument is 0. It should be scaled by a scalar, by the absolute value of the scalar. And it should satisfy the triangle inequality. Okay? Again, I implore you, go and look up your linear algebra books, because I'm going to take your first year university for granted. You might not like the idea of forgetting stuff, but that's the reality of it. Just go and look up your first year textbooks. Okay? Or second year, depending on how you did it. All right. So these are definitely positive. So the sign of the inner product depends only and only and only and only on that on that cosine term. And the sign of that cosine depends on its angle argument. Okay? All right. So we call it the descent direction if this inequality holds. So what it really means? P is vaguely in the opposite direction to the gradient. Okay? So the angle formed between P and the gradient is larger than pi over 2. I mean, and the other way as well. Now, often we pick this direction to be the product of the gradient and some matrix. I call it BK inverse. It can be, I mean, I could have called it, I don't know, CK. But I picked BK and put an inverse on top of it to really connect it to other ideas later on in this lecture. So that's usually the form that we look at. The search direction will take a form that looks like this. Now, if I'm going to pick a form for the search direction PK that looks like that, give me a condition. Think about it for 2 seconds. What condition we need to satisfy so that a search direction given by this equation is a descent direction?
BK and three positive dominant.
That's one thing. It is semi-correct. That's correct, because semi-definite you couldn't have inverted it. It would be a singular matrix, can't inverse. Okay. So Mark has a suggestion saying BK should be positive definite. If BK is positive definite, it means its inverse is positive definite as well. And then we definitely will have a descent direction. My next question is why? It's correct, but why?
Because if you substitute PK transpose A, the gradient of FK is just a norm. And then it's also positive definite.
Now let's step one step at a time, because you jumped ahead and you didn't jump ahead quite correctly. Let's just replace PK with this value in this relationship. I end up getting okay, so that would be the relationship, right? That the inner product would be equal to this. What is the property? What was the property of BK inverse? So what is this transpose? Okay, you guys don't answer. What is the transpose of a positive definite matrix? Okay. Roshan, do you know what is the transpose of a positive definite matrix? Moore, do you know what is the transpose of a positive definite matrix? Elena, do you know what is the transpose of a positive definite matrix? Yes, but if I give you A, and A is a positive definite matrix, I say, tell me what A transpose is. Do you know what it is? Ethan, do you know what the transpose of a positive definite matrix is? Didi, do you know?
Is that itself?
It is itself. Why?
Is positive definite symmetric?
It is symmetric. Any positive definite matrix, the way that we are defining it is symmetric. You can have, depending on how you define it, for other intents and purposes, they are all the symmetric. Okay, so this transpose term goes away. Is itself. Now, I'm stumped. What should I do now? I have this vector multiplied by some positive definite matrix. I mean, transpose, and then it multiplies itself. Hmm?
spectral theorem to decompose that.
Yeah, we can go down the path, correct. But that's really where it ends up. The definition of a positive definite matrix is this. A matrix is positive definite if, a matrix A is positive definite, if I multiply from the left and the right by some row vector, and then it transposes on the right, if the result is positive for all choices of x, then the matrix A is positive definite. Okay? Again, we are in Rn, so all these x's are in Rn. A is in Rn by n. Everything is nice, right? This result is scalar because matrix, row vector, column vector. This thing is scalar, so I can say it's positive. Makes sense. Now, this in a product, forget about this negative. This is positive definite. Just these gradients are just vectors. Call them v, and you call grad of f at point at xk v. So if I'm really computing v transpose bk inverse is positive in matrix times v. It is positive. Has a negative sign behind it, so the whole thing is negative. Right? Okay. So really, bk needs to be symmetric and non-singular. Again, as I said, ideally we would like it to be positive definite. Sometimes we work with things that are non-positive definite. But there is a good reason for it. We will talk about it. Now, depending on how we choose bk, we get different members of the line search family of algorithms. If we set bk to be identity, we get pk to be exactly the negative of the gradient, and that belongs to the. That's what we know as the gradient descent algorithm. If we pick bk to be the Hessian at point xk, then we end up getting the Newton's method. And then we can try to approximate the Hessian, which is really the focus of the majority of the next lecture. I will spend a lot of time on how to approximate the Hessian to get the benefits of the Newton's method without some of these drawbacks. And again, we are going to mainly focus on the cases where pk is a descent direction. All right. Good. So from a point of view focusing on solving optimization problems, the main objective here is then how to choose alpha k and pk so that we know we are going to converge to a solution that satisfies the necessary and sufficient conditions potentially. And then study the convergence behavior, so in terms of the rate for special cases of steepest descent, quasi-Newton method, and Newton method itself. So that will be the objective. I keep reiterating it because I want you to hopefully understand why we spend so much time on understanding certain behaviors and properties. The reason is that then we can design algorithms that take advantage of those properties and behaviors. Now, we talked a bit about pk, but let's not talk about a bit about the step size. That's okay. Okay. So at each step k, what is really desired is to pick some step size, alpha k, so that we shrink the value of f at the new guess point as much as possible, to make it as small as possible. Right? So that's the idea. I want to make decisions for each iteration so that I push the value of the function to be as small as possible. Okay. That makes sense, hopefully, right? Does it make that intuition? Does it make sense to everyone? It doesn't make sense to anyone? No one has any opinion of any sort?
What's the condition on F?
What do you mean?
So, say it's
Let's assume F is the nicest thing you can imagine. You can infinitely different. Wouldn't matter in the end, but at my point xk, I'm given a direction, and I want to find the step size. Greedily, I want to follow that direction as much, for some distance, so that I end up at a point that the value of function is the smallest possible value I could have found, right? Of all the points that I could have traveled along that direction. That's the idea. So ideally, I want to pick my step size to be the argmin. Now, what does argmin mean? Yeah, the value that minimizes whatever expression is on the right-hand side. So the step size alpha k is what minimizes f of xk plus alpha pk. So given the guess point that we are, xk, and a direction that we are going to travel along, we want to see how far we should travel along it to get the smallest value of the function f. Right? That's the idea. It's a stepsize selection question. Now, so that's one thing. Now we're getting into a catch-22 territory. To solve an optimization problem, we end up solving another optimization problem. If we want to go down that path directly. But maybe someone just, it's the first idea. But one argument is, maybe that problem is super easy to solve. The original problem is not. But that's an idea. But solving this problem might be as hard as the original problem. So there's nothing to be gained. Now we have to construct another line search algorithm to solve this other problem, and then it goes ad nauseum. But it can be approximately solved, maybe, using some bisection method. We can pick a large alpha, evaluate the value of that function, halve it, evaluate the value of the function. If it was a smaller value, then forget about the original one. Keep halving it until we get to an interval that's smallish. That's one way of approximately solving it. And in general, this sort of... Now, I can call this value as a function of alpha. I call it phi of alpha. Because given the values of xk and pk, it's just a function of alpha. So I can draw it. It might look like this. Okay. Now we can solve this, whatever. But let's see, if I don't want to solve that problem, how can I pick an alpha k that has some nice properties? Okay? So if you don't want to solve that exact step size selection criteria, the one property that the step length should have is it should result in a value of the function that is strictly smaller than the previous value. Otherwise, we wasted an opportunity. Either we really don't want to, potentially in this sort of method, we don't want to go somewhere that increases the value of the function. And definitely we don't want to remain stationary as well. So we want to have some reduction. Okay? slide, and there is an example for that scenario, but really that condition on its own is not enough. A mere reduction is not enough. Now, do you want to spend some time looking at that example and someone tells me why that condition, just some strict decrease, is not enough? If it ever gets to the point, it might take too long, but there is a bigger problem.
The speed is very big.
Sorry?
The speed is very big.
No, I mean, it can be small or big. The problem doesn't necessarily depend on the value of the step. Just look at the example. I have a function, quadratic function in x, very simple, x squared. I start from some initial guess -1 here. I pick the step, the search direction pk is -1 to power k. If you write it, you realize it's a descent direction, so it's good. Then I go and pick some ridiculous step size selection. See, it's a counter example, so I've constructed it to look like this. And you will realize you can show that every step, the value of the function is strictly less than the previous value. So in the language of sequences, if I construct a sequence called, and let's call it EK, what do we know about EK? Let's put it the other way, it makes it easier. Yeah? You can conclude another, you can conclude something else as well. Now let's not do it like this because this doesn't help. Let's look at the sequence of FKs directly. What property do they have? They are decreasing, right? Okay. Are they bounded from below? Yes, because x is bounded from below by 0. Now, if I have a decreasing sequence that's bounded from below, what do I know about it? It converges, but not to its minimum necessarily. That's the key. It will converge somewhere, but we don't know where it will converge. So in this scenario, it will converge, I think, somewhere around 1. In again super vague description, the step size runs out of oomph. It doesn't push the sequence, push the function to be becoming smaller than the value that we need. I mean, continuously being smaller and smaller. Okay? So the strict step size is not enough. So what is the remedy? So we just noticed that if we just enforce strict decrease, it might not be enough because the value that we are decreasing might become vanishingly small. So how can I modify that condition to circumvent this problem? Yeah, that's a good idea. I can stick some negative value on this on the right hand side and say, okay, I have to really get the decrease, which is I have to get enough decrease. Okay, so that's the idea. We are building that idea. Good. Now that term that I put it the other side, but it doesn't matter. The term that we have here, this is my minus epsilon. Why can I say it as minus epsilon, really? Because I know the inner product of the gradient and pk is some negative scalar, so that's this summand is negative. Now there's a reason the peak is something that looks like that, but that's the idea of I want it to be small enough. Okay? Okay, so now there are these two ideas. The step size should be small enough to result in a sufficient decrease. And then it should be large enough so that we don't get stuck. Okay? Now the way that we represent this sufficient decrease by adding this new term. And again, if we stare at it for 10 seconds, we realize it depends on some constant C1. That's constant. We don't need to worry about it. But it is proportional with alpha. And it is proportional to this directional derivative. The value of the directional derivative. This condition is known as the Armijo condition. It's probably the most famous condition in numerical optimization. And in practice, we pick this C1 to be very small. Okay? So that's one idea. So now the idea that we've seen so far is that we have to pick the step size so that we get a sufficient decrease, but not too small. The way to enforce it is to make sure that that inequality is satisfied. Now the Armijo condition has another condition associated with it, but let's just construct it for a bit. Using some algebra and previous algebra. Now, let's define this function L of alpha as f of xk plus c1 times alpha in a product of the gradient and pk. What is this function? What does it describe? It's a function of alpha because xk, pk, and c1 are given to us. Is it a hyperbolic curve? It's a straight line, right? It's a line. Because it only depends on alpha. So if I just call, I can write it as this, right? And B is a bad idea. Maybe it was a bad idea. D plus alpha, and I need some coefficients, I don't know, gamma. This looks like this, right? I call it y. That's the equation that it describes a line, right? In alpha. So if I draw it, it looks like this. setting alpha to equal to 0, it means I start at f xk. Okay? So if you go and look at the Armia condition, what was it? It was right? So I called the right hand side L of alpha, and the left hand side we already called it phi of alpha. So the Armia condition really corresponds to all these intervals in which the curve phi of alpha lies underneath L of alpha. So the L of alpha is this line. That's the curve. So all alphas in this interval satisfy the Armia condition. All these alphas in this interval will satisfy the Armia condition as well. Here they won't satisfy it because phi is larger than L of alpha. Okay? So one observation is the Armia condition is always satisfied if we pick alpha to be small, for very small values of alpha. Because as I decrease the value of alpha, I move to the left on this axis. In this vicinity, the line is always above phi. Okay? Now, before we continue, what is the impact of choice of C1 on this line? So tell me what happens to that line if C1 becomes very small? Did you said something? Okay, it becomes horizontal, right? So what is the implication of that? Potentially there are larger intervals in which the Armia condition is satisfied, because we are lifting this line. Okay? So that's what I said. When we say in practice you pick C1 to be small, that's what it means. I mean, that's the interpretation. It's important to connect these things, because we want to give ourselves enough freedom, really. All right, but as I said, the problem there are two. There's another element, because we don't want to pick alpha to be too small as well. We want it to be large enough, otherwise we will get stuck. So that leads to the second condition. It's called the curvature condition. What is the curvature condition? Okay. All right. The curvature condition looks like this. Now let's see what it really means. What it means is before we go, remember phi of alpha is so how do I take, I want to calculate the derivative of phi of alpha with respect to alpha. What is the derivative? How many of you remember the chain rule? Okay, those of you who can't remember the chain rule, go and look up your calculus books. Okay, it's, again, we will take so many derivatives in this subject. I really want you guys to follow this, right? I try to refresh your memory, but you will not get anything out of this subject if you don't brush up on your fundamentals. And they are not advanced ideas, right? It's important that you go back and look up basic calculus. Okay. So if I have a function that looks like that, how do you take its derivative? Roshan, can you help me?
Derivative of f multiple pk.
Okay.
Derivative.
Yes.
Sine
So we take the derivative with respect to the argument and the derivative with respect to the function. We multiply them somehow. So it ends up being this. So if I take the derivative with respect to alpha, if I just use dash, it becomes grad of f because pk is the derivative of the input argument with respect to alpha. Okay? So that's what it is. So this condition, what it really says is the slope of the function, slope of phi at any point alpha needs to be greater than c2 times the initial slope at point 0. Okay? So that's what it means. So here, for instance, this is that c2 times initial slope. Okay? So I have a slope there. Do we accept this neighborhood or not? No. Why? Yeah. Slope is, in magnitude is larger, but in considering the sign, it is less than that relationship, right? It's steeper. So we discard this neighborhood, and it automatically chops off the nasty two small alphas. Okay. So we don't need to worry about it. So now acceptable neighborhoods in this graph are, for example, here. And then here. Okay? Now if I put these two conditions together, the Armia condition and the curvature condition, I just can write them in one box there. Together we have something that we know as the Wolff condition. Now some observation is we can find some step size that satisfies the Wolff condition, but is not necessarily close to the minimizer, the exact line, the exact step size selection rule that we talked about. But that really doesn't matter. In the end, with these we have some guarantees on performance that we will see. There is another version of this condition which we call the strong Wolff conditions. Surprisingly, it just means they are stronger. So there is another inequality on the other side of the second curvature condition, so we just capture it with those absolute values. So it really stops us from picking alphas for which the derivative of function is too positive as well. So we don't overshoot things necessarily. Okay? There are other conditions as well. Did I put it here? Do you see that? Doesn't matter. Okay. So now these are Wolf conditions. Again, we are looking at it from designing an algorithm. Before we go on a 5-10 minute break, let's say 5-minute break, can someone tell me if you're going to design an algorithm and you have to pick alpha, and I tell you that your alpha it must satisfy these two conditions, what worries you?
It's a problem to solve.
Yeah, okay. There is even a more fundamental worry in my view. What if I can't find an alpha that satisfies these conditions? Right? The good news is that there always exists an alpha, so we are going to show it after the break. So come back here around 10:15. Cool. Let's see the satisfiability conditions. So the starting assumption is f is differentiable, otherwise the gradient wouldn't make sense. And let's assume p is a descent direction at some point xk, and you're going to assume f is bounded along the direction we are trying to optimize, otherwise, again, the problem wouldn't make sense. It would go to infinity, negative infinity. We are putting the assumption that C1 is less than C2 because up to now, we see the conditions here, but I haven't said why. So here there is an ordering. C2 should be smaller than C1, C1 should be less than 1, both of them larger than 0. And we're going to see why. So we're going to make this, enforce this condition in this theorem. So the idea is that there exist intervals of step lengths satisfying the Wolf condition. Similarly, we can show this, it satisfies the strong Wolf condition as well. Now, why do we care about intervals? Because if it was one point in isolation that was going to satisfy the Wolf condition, it would have been, again, layman terms, it would be bloody difficult to find it. So we want to find an interval so that if we hit around somewhere vaguely in this vicinity, things are good. If we want to be fancy, is that the measure of the solutions is non-zero. But that's just a fancy way of saying there's an interval. Okay? Now let's see. We have L and we have phi alpha. The first statement is that they will intersect. It's not quite precise what I've written there, but they will intersect at alpha equal to 0. That's trivially that is true. But they will intersect either at one other point or they won't intersect at all. Okay? It wouldn't make sense that they won't intersect at all. Eventually, in the limit, they will intersect. Okay? Now, they might have multiple intersections as well. Let's just intersect at one point. The closest one to 0 is non-zero. In the picture that we have seen before, it means here. So in that interval, any point less than this intersection point, the Armia condition is satisfied. It's by construction. So let's call that point that these two curves, the line and the curve, intersect alpha dash. And what it really means is the left-hand side, which is phi of alpha dash, is equal to the right-hand side, which is L of alpha dash. Right? Clear so far? And we know the Armia condition holds for any choice of alpha smaller than alpha dashed. So Armia condition is satisfied in this interval. Now, from the mean value theorem, how many of you remember the mean value theorem? How many of you remember the Taylor's theorem that we introduced last week? Okay. You know, the first item of the Taylor's theorem is the mean value theorem. So, again, connecting. Mean value theorem is probably the second half of your first calculus subject. Can someone remind everyone else what it means? For a scalar function, right? Argument scalar, everything is nice. So it means if you take an interval, alpha and beta, evaluate the function at these points f of alpha, f of beta, and say, okay, f of beta minus f of alpha divided by beta minus alpha, then there is a point in that interval that the value of the derivative is the same as the slope that we just calculated. That's what the drilling means. Okay? Now, from the mean, applying the mean value theorem to the interval alpha dash and 0, there exists some alpha double dash in that interval that this relationship holds. So look at this. This alpha dash, if I just, not to confuse it so much, if I divide both sides by alpha dash, that would have been it. What was this? Was the derivative of some. So there exists some alpha double prime point that this relationship holds. Okay? Now I have equation 1 and equation 2. What can I conclude? I move this to the right. This is equal to this. Then it means this. Right? Now, what happens if I replace C1 here with C2? Just clean it up. So my question is, what happens if I replace C1 with C2? If I have a number minus 5, if I multiply it by some positive number, what happens to it? It becomes more negative, right? Now if I multiply it by two positive numbers, one is, call it C1, and the other one is C2, and I know C2 is less than C1. What can I conclude from this relationship? Which one is more than that? So, is minus 5 C1 less than or larger than minus 5 C2? Okay? Now let's apply this logic to here. What is the sign of this inner product? It's negative. What is the relationship between C1 and C2? C2 is larger than C1. So what happens to that inequality? Now, what should I replace? So I should replace this equality with something. What should I replace it with? We end up getting larger than, right? Because C2 was larger than C1. So be negative. So we made the right-hand side more negative. Okay? Ta-da. So we constructed now anything in that interval now is fine.
Greater than or equal, or just greater than? Is C2 strictly greater than C1?
It would be, yeah. It's strict, yeah. Okay? And in that vicinity, we can perturb things are continuous. There exists a neighborhood now that this relationship will continue to. All right? Cool. Some observations. If I multiply the objective function by some constant, or make some affine change of variables, the Wolf conditions don't change. You can work it out yourself, but that hinges on you knowing what an affine change of variable is. Can someone tell me what an affine change of variable is? Plus something. Otherwise, that would have been just linear. So if I don't know, an affine map takes its argument from the left, multiplies it by a matrix, and then adds a vector. That's an affine. There are other ways of writing these sort of conditions. There are different versions of these conditions. That's another example here. You can look up your textbooks on page 36. There are the Goldstein conditions for step size selection. The Wolf conditions are the most famous one, but there are other ones as well. The disadvantage of Goldstein is they may exclude the minimizers of phi, the exact minimizers of phi. And they are used often in Newton-type methods, but they are not really suited for quasi-Newton methods. Now, all these observations are very empirical. I don't know why. It's a good question to ask. I don't know if you will have an answer, but it would be interesting to know why certain algorithms behave better in the presence of one condition versus another. Now, where are we? Okay. So far we talked about search direction, what it means to have a descent direction, and then we talked about step sizes. We said that a step size should make things small enough without it becoming too small. Now, that's one way of implementing. If you're writing an algorithm, that's one way of implementing a subroutine to find the potential step size. We use the backtracking approach, and we don't enforce the curvature condition explicitly. We cross our fingers and hope. The reason is, if I start, the reason that we introduced the backtracking, the curvature condition was to make sure that our alpha is not too small. So the idea is that if I start from a very large initial guess for my alpha, hopefully I will hit an interval that satisfies the Armia without it being too small. So that's the intuition behind it. So we start from an initial guess, we check if the Armia is satisfied or not. If not, we shrink it by some factor rho. And we repeat it. So we shrink it until we get to a point that the Armia condition is satisfied. We can change the contraction factor in each iteration as well, depending on the problem. So these sort of choices become very problem specific. And then just something that in near-term methods, if you're implementing a backtracking line search, we start with a guess of 1. But they shrink. All right. Now, we talked about search direction, step size. Not an important question. We want to know what happens to these sort of line search methods if I pick a step size that satisfies those curvature conditions and pick a search direction that is a descent direction. What can I say? Right? So we get some definitions. The angle between two vectors, between pk and the negative of the gradient. This is the cosine that we saw before. Just again refreshing your memory. And then the idea of a level set and sublevel sets. So if I have a function fx, the level sets corresponding to fx equal to c are the points x that satisfy this equation. We call them level sets. The sublevel sets are all the points that satisfy this inequality. As an example, if my f is a circle, the level sets corresponds to points on a circle for different radii. Sublevel sets become the interior of these circles as well as the surface. Okay. We saw the definition of Lipschitz conditions last time. We repeated. What it really means is you can define it over a subset of X of the whole domain. We are saying X, if I pick 2 points X and X bar and evaluate the value of function at X and X bar, calculate the difference, the magnitude of the difference is upper bounded by some constant L times the distance between the 2 points. So it really says the variations are not too, the function doesn't vary too much. All right. Now the convergence of line search methods depend on 2 factors: step length, so how we picked at the step length, and the search direction. Now, a very odd theorem. It's pretty interesting. The Zuttendijk results. So let's just read it. So if you pick any line search iteration where P is a descent direction and alpha k satisfy the Wolf conditions, so that's the hypothesis. Furthermore, we want F to be bounded below. Why do we want that? Yeah. So because if it's not bounded below, again, we are solving a silly problem. It's infinity. It doesn't make any sense. We want it to be continuously differentiable so that when we talk about gradients, it should make sense. We are interested in looking in the interior, in the behavior of the algorithm in some sub-level sets that is defined by the value of the function at the initial guess. We further assume that the gradient itself is Lipschitz continuous on n as well. So the gradient doesn't change too much. Then we have this result. So the series constructed by the cosine and the magnitude of the gradient is bounded. Okay? So if you just look at it, it says, well, great, but what does it mean? Can someone tell me what it means? How we can use it? If you go to the next slide, if you have it, you will see how you can use it, but don't do that. Focus on the cosine term.
Converge is perpendicular to the right direction. Like, it's not going in the...
You are so close.
It needs to go perpendicularly to the angle of steepest descent for cosine term to be 0.
We do not want it to go to become perpendicular to steepest descent.
Looks like it is.
No, it doesn't. It means if we multiply, that happens. Now, if I enforce a condition so that this cosine is not 0, is bounded below, then the series constructed by the norm of fk has to go to 0. Okay? Because if now I say I make sure that P is picked in a way such that that cosine, that angle, sorry, that the cosine is away from 0 by some delta, because, again, refresh your memory, if I have a series, I don't know, ek, I know it is bounded, it is necessary for ek to go to 0, right? Otherwise, the series wouldn't be bounded. So this is my ek. I know this will go to 0. Now, if for any point this guy is away from 0, like that delta, then this term has to go to 0. Okay? So this becomes the condition. So I have to make sure I don't become, my search direction is not perpendicular to the gradient. When do we have it for free? If pk is exactly minus grad of f, we always have that condition, right? With the same direction. Correct? So really, as long as the search directions are never too close to orthogonality with the gradient, we are fine. We always converge to a stationary point. What's a stationary point? A point at which the gradient vanishes. Again, there is no guarantee that this converges to a minimizer. It is attracted by a stationary point, and we can always have other discussions. What stationary points are attractive? They happen to be minimizers for this sort of stuff. Okay. So if you introduce a bit of noise, then we always end up in a minimizer. Is it a global minimizer? No. It's a minimizer in that sublevel set that we introduced in the statement of the theorem. Sublevel set. Oh.
That's going to lower its rating.
Yeah. Jesus. It's not to be. The sublevel set was this. So as I said, if pk is peak to be minus grad of f, we end up with steepest descent, we converge to stationary point, and if the step size is satisfied, I mean, under the condition the step size is satisfied Wolf or Goldstein's condition. Now let's be a bit more adventurous, so look at the Newton-like method. Even though you haven't seen Newton method yet, you will see it, but let's just ease into it. So a Newton-like method looks like this. It has that BK inverse there. Now, if you make an assumption that this BK is uniformly bounded condition number, and that uniform band is called M, then we can start arguing if cosine of theta k is strictly larger than 1 over m, then we have the same statement. Now, to make sense of this, please raise your hands if you've heard the term condition number of a matrix. How many of you have heard the term singular values of a matrix? You're not sure? You heard it? Kinda, maybe?
Come through over.
Okay. Again, that's another sign that you have to go and look up your linear algebra texts. Because I would be very surprised if there exists ever a linear algebra subject that doesn't cover singular values. We will cover it later on when I talk about these squares. I'll just remind you, but it's very important. Anyways, condition numbers are okay, in terms of when we have symmetric matrices, you've heard of eigenvalues of symmetric matrices, eigenvalues of matrices, right? Has everyone heard of eigenvalues of matrices? If I'm dealing with a symmetric matrix, it becomes a bit easier to talk about it. Think of it as the ratio between the largest and the smallest eigenvalue of a matrix. I'm really abusing the notation a lot here. They are related to singular values of these matrices because they are symmetric. And that ratio is called the condition number. Now, condition number shows itself whenever we want to understand the numerical behaviors of some algorithm that deals with matrices. Whenever we want to solve a system of linear equations, the thing that really determines if the solution that we are going, it's easy to get the solution, or if the solution we are getting is sensitive or not, is the condition number. That's something you can remember. Now, if this ratio, the assumption is that if the ratio of those singular values, eigenvalues, is less than m, then I have to make sure my search direction is the cosine of the angle between the search direction and the negative of the gradient is larger than 1 over m. If that's the case, then the sequence converges to a stationary point. Okay, so that's a bit more general under another assumption. Now here I'm talking about the concept of global convergence. This is not saying that I will converge to the global minimum. What it means is if I start from anywhere in the domain, I'm going to converge to a solution. So I'm globally converging. Doesn't mean I'm converging to the global solution. I can have local convergence, global convergence. Global convergence means wherever I start my algorithm is going to converge. Local convergence means there is only a set of which if I initialize my algorithm, inside that set I'm going to converge. Okay? So that's something that's very important. You should not mistake these things with each other. Now, ideally, whenever we design an algorithm, we want it to converge whenever we initialize it. But one observation is this global convergence usually yields slower convergence rates. So there is a trade-off. Okay, so it's an observation that you have to make. For instance, the steepest descent method is globally convergent. It's nice. Whenever you start it, it will go somewhere if you pick the steps out correctly. But it is slow. There is a quantifiable slowish, depending on the function. A pure Newton method, as we will see in the next hour or so, it converges very fast. If it converges. So you pay a price. Okay? Now the challenge is to design and choose algorithms that provide the requirement that you want. Now let's start by looking at the convergence behavior of the steepest descent method for a very simple class of functions. Let's start understanding the behavior of the steepest descent when we want to solve a quadratic problem. So the cost function is f, given by that. The grad is, taking the derivative, becomes qx minus b. And we know the solution is, the minimizer is q is a solution to this system of equation. Now, some smart person might say, oh, okay, so if that's the case, I just calculate this, I'm done. Why do I even care about optimization algorithms? Those are dramatic. What is the problem with that statement? Because they might say, oh, it's one line of code in MATLAB. What is the problem with this statement? Is there any problem with that statement first?
An
No, but they will say it's one line of code in MATLAB. Yeah. People sometimes forget that under the hood of these solvers, there's a lot of numerics that happen. There is an iterative algorithm underneath that tries to solve the system of equation. These sort of optimization methods that we talk about are yet another method for solving the same system of equation. Okay? And yes, there are issues. The inverting is the main challenge here. So you need to have an iterative algorithm to invert the matrix. If your matrix is ill-conditioned, so if that condition number I was talking about is large, then you will have a lot of problems in doing the inversion in a stable, so that your numerics are stable. Okay? So don't be one of these people. Don't treat functions and methods that you just see in a software package or something like MATLAB as just don't take it on the face. Just try to understand what happens underneath. There's always algorithms that happen underneath. Things are happening there. Sometimes it helps if you understand them. Anyways, let's talk about let's go back to our method. We want to come up with an iterative method to solve that optimization problem. We pick the step size alpha k, and we do the exact line search. Now, the good thing about the exact line search of a function like this is you can take the derivative of this. So what is the derivative of f of xk minus alpha grad of fk with respect to alpha? Chain rule, right? So what is the derivative? Anyone? So I have f d. So if I want to take the derivative with respect to alpha, what does it become? Sam? Right? You good with that? I'm just trying to think of what is the best way of plug it in. Now let's plug this here. I can't remember if it's the best way, but let's just multiply stuff. Okay, yeah, it's good. What is this? It's minus. I made a sign mistake somewhere. Let me just go back there. I think they made a sign mistake. There's a minus there. Okay. Yep. Yep. Yeah, no, it's correct. So this thing is minus multiply stuff becomes I enforce the first order necessary condition for optimality. So this should be equal to 0. So alpha, the best alpha is that. Let's see if it, yay, agrees with what we have here. So that's where it comes from. I just plug it in. This is my step size. I'm sorry, yeah, step size. The best step size I can pick for this problem. And that's the iteration I have. Okay? So this is the exact line search algorithm for a quadratic problem. And if I just replace the grad in terms of q, x, and b, just requires a bit of multiplication, and I can have a closed form iterations in terms of xk, for xk plus 1. Okay? So good. No, something I just remembered. If you go down the path of the exam, I really don't care about little mistakes of signs. As long as you know what you're doing, I don't care. You don't need to keep track of all. I mean, you should be careful, but you will not lose a lot of marks if you have a little mistake of forgetting carrying over plus minus. That doesn't bother me. But something that really bothers me is a mistake like this. So if you are given a problem that looks like this, and it has, I have seen it, otherwise I wouldn't talk about it. And then if you say x is that, you will get 0. Because this doesn't make any sense. Okay? So just try to make sense. Anyways, that just reminded me. Then we can try to establish more results in this setup. So now we have these iterations that look like that. And then we say, okay, let's define this weighted norm. Okay? So the weighted norm definition we work with is x transpose qx. And then one observation is that this weighted norm has a relationship to the original value of fx and fx. Fx star, x star is the solution. So now we can show. Now if I call this my error sequence, ek plus 1, then I have this relationship between ek plus 1 and ek. Now this is, I think this is another question in your homework. You have to show this. It's not hard. It takes time, but it's not hard. It takes time to warm up into it. It's not, once you're there, it's not really hard to do. Now if we show, we use the method to solve a quadratic problem. Here I talk about strongly convex quadratic problem. What you really need to know is it really means Q is positive definite. We talk about convexity in 2 weeks' time. And then we can show this relationship holds. So the error sequence at time k plus 1 is bounded by error sequence at time k with this factor. Now, if lambda 1 is something, and lambda n is the largest eigenvalue of Q, lambda 1 is the smallest eigenvalue of Q, because it is positive definite, lambda 1 is strictly larger than 0. And you can, it's very easy to see that, no, let me, is this ratio larger than 1 or smaller than 1? Han, is it smaller or larger than 1?
Smaller.
Why?
The first term is less than 1.
Which term?
And lambda n minus lambda 1, or lambda n plus lambda 1.
Yeah, I mean, that's what is. That was the statement. The numerator is smaller than the denominator, and it's positive. There's a square root in there, anyways, doesn't matter. So it's less than 1. So what do we know about a sequence that looks like that? It converges, and on top of it, it converges to 0. On top of it, it converges with the Q linear convergence rate. So the convergence is of order of linear convergence for steepest descent for these type of problems, which are probably the nicest type of problem for steepest descent. In 7-8 lectures in the future, we will revisit this result and really talk about, try to generalize it to a family of strongly convex Lipschitz gradients functions in the presence of constraints. So not only the quadratic problem, but that's something that we see here. So the convergence looks like this. Now going back to the idea of condition number, it shows itself here as well. If the condition number is large, so it means lambda n is much larger than lambda 1. Let me step back. So condition number being large is lambda n much larger than lambda 1. Now what happens if lambda n here becomes very large? It gets closer and closer to 1, correct. And remember I showed you an example about converging sequences when the factor was close to 1. The practical convergence becomes very slow. So even though the order of convergence is linear, practical convergence is terrible. So this is the general statement for strongly convex functions. Again, don't worry about it now. strongly convex functions are there are functions that kind of look like quadratic functions. So I can put a quadratic function underneath them and it forms an envelope. That's one way of thinking about it. And for those methods, we have this sort of convergence rate as well. But again, the key is if the condition number is too large, the convergence is terrible. Very slow in practical terms. If the condition numbers are large, the initial point that we initialize the problem for algorithm plays a very important role in its practical behavior. Because if we initialize it, so when we have condition numbers that are large, you can think of them, it corresponds to ellipsoids. So if the ellipsoid is very elongated, it means the condition number is large. Now, if we initialize the solution somewhere like that, the iterations behave nicely, they converge. But if we initialize it along this side, we will have some pronounced zigzagging behavior in the practical implementation of the algorithm. So even though we will have still convergence, the way it manifests itself becomes sensitive to where we initialize the algorithm. But again, these are the steepest descent algorithms. They always converge if we initialize them anywhere, unless, as long as we pick the step sizes properly. The way that the algorithm behaves might be different. Okay? But in Newton's method, we won't have global convergence. So it really becomes important how we initialize the algorithm, so to get to have that convergence. Okay, let's come back at 11:15. So we go and have a look at the Newton's method. Now, just to refresh your memory, if the goal was to solve this using Newton-Raphson's method, how would we proceed? We would start with some guess, solid x naught, and then what would we do? Yeah, I would find the derivative at that point, construct a line that is tangent to the curve fx at that point, find the intersection with the x-axis, right? Then what would I do next? Yeah, I would go and look at this point, then I would go and do the same thing again and repeat this process until I find the solution, right? Hopefully if I started in a nice spot, I would get to the solution. Now, just here, it's easy to see. If I had started from this point, the line would have intersected the x-axis somewhere over here, right? And then if I'm lucky, I would converge to this other solution. Sometimes I might just go, I don't know, nowhere. So if, for instance, if I extend this function to look like this, now this is good. I can't think of a way to draw it, I might end up getting further and further away from the solution. So this is, it's sensitive to the starting point. Now let's just, before going forward, let's try to figure out how the iterations for Newton-Raphson's look like here, right? What is the, so if I'm given x naught, so I am at point x naught, and f of x naught, what is, how can I calculate x1? I know I am following a line with the same slope as grad of x naught. So the same normal. So what is the equation? What is this?
Sorry, what do you want to do?
I want to find a relationship for x1 in terms of x naught. And the, sorry, I should have used the capital F here. And in terms of capital F of x naught and in terms of the derivative of x. And you can start thinking fx as a scalar, but it can be a vector. So we want something that is general.
Equation with the gradient that intercept the initial point.
Sorry, what?
A linear equation.
So how do I write it? I just want to write that linear equation. I want to write x1 in terms of x naught and this grad f x naught. And in terms of f as well.
Just to the 2D things, y minus y naught equals the gradient of x minus x naught.
Yeah, that's the starting point. Okay. So what is, let's assume it is, f is a scalar function. So what is the value of the line at that point? It's 0, right? So f of x naught minus 0 is what? Equal to what? Right? Yeah, we're good. It doesn't need to be a 2D thing, right? This relationship holds in any dimensions. That's why I wrote it as in terms of an inverse as well. So if, now again, if f is a vector, what is grad of f? It's a matrix, it's a Jacobian. Right? That's why I wrote it as an inverse. So that's Newton-Raphson's method. Very brief Newton-Raphson's method. Now, if I want to solve grad of fx equal to 0, so what I'm really saying is that capital Fx is really grad of little fx. What I showed you was the iterations look like this. So in this language, it is xk minus second derivative of xk. Right? Good? All right. Now, let's see. I do this, then I show you some stuff. All right. So now there are 10 billion different proofs for Newton's method. Everyone has their own opinion about Newton's method. That's the result that is stated in your book. The idea is this. If the Hessian is Lipschitz continuous in some neighborhood of the solution, and it says it requires x star to satisfy the sufficient optimality conditions, then if we start close enough to x star, whatever that means, we are going to converge to x star. The rate of the convergence is quadratic. So it is 1 order of magnitude faster than the gradient descent. And it, of course, additionally shows the derivative, the sequence of derivative converges to 0 as well. So this is one result. I'm going to show you another proof, which I like more, because it's a bit more constructive and doesn't rely on this sufficient optimality condition. So I'm going to construct it now. It is uploaded to your LMS as well, but I'm going to redo it now. Okay, so it starts like this. Let's assume there is some positive h such that, so I'm going to make my life easy. I say capital H of x is Hessian of f. So I'm going to write it like that. So first I'm going to set up the hypotheses of what I want to show. I'm going to assume that's the first statement. I'm going to assume norm of the Hessian at some x star. The Holm of Hessian inverse at some x star is less than 1 over some positive h. Additionally, I assume the gradient vanishes at x star. Now, does it mean that x star is a minimum? No. Does it mean it's a maximum? No. It is just a stationary point at which the Hessian norm, the inverse of the norm of the inverse of Hessian, is upper bounded by some 1 over h. Now, if you see a matrix, now that's why, again, we talked about norms. Some of you couldn't remember vector norms. Now I'm going to talk about matrix norms, operator norms. How do I define a matrix norm? Sorry?
Is it the operator norm?
It's the operator norm, exactly. So how do I define it?
One of it is super norm that divided by
Yeah. There are different ways of writing it. All of them are equivalent. One is sup of all x's. So if I'm doing the norm of a, for instance, okay? So that's what it means. This norm is induced by this vector norm, for instance. So go and look it up. There are different, again, I said there are different versions of writing it, but that's one way. You can, instead of having that term in the denominator, you can restrict the set of x's that you look at to those whose norm is equal to 1. Now we have that. Then we are assuming there exists some beta and some L such that we start close to x star. If we are in the vicinity of x star, then the Hessian is Lipschitz. And then we say we want to be close to the solution. So that's the that's local thing. So I want to be closer, the neighborhood of x star, some ball around x star of radius gamma. Now this gamma looks a bit funny, it looks like this. It's the minimum of, now this comes out of the proof, we will see. So if I start in this neighborhood, then I'm assuming I'm starting in that neighborhood. So these are the given things that are given to us. Okay. Now, if these things hold, then these things happen. One, I'm going to define my iterations first as this. So I'm dropping dependence on k, and I use this plus superscript to show the next iteration. Again, it's a shorthand for xk plus 1. And everything else, there's a k here, there's a k here, there's a k here. Just a shorthand way of writing it. So what we can show is this. I get, in consecutive steps, I get closer to the solution, strictly, and remain in that neighborhood of gamma. So that's one thing. The second thing is, doesn't matter. The second thing is really the first thing we will end up showing, but whatever that means. It's the intermediary result to just help us show other things. And then 3 is the quadratic convergence. Okay. So these are the things that we end up showing. Okay? Now, to be able to do this, we need 2 auxiliary lemmata. One is this. And both of them, you have to show it in your homework as well. So, if I have a matrix M, and M is symmetric, I'm not sure if you need symmetricity, but yeah. You do. Show then. If and only if so if inverse norm of something is less than 1 over h, then the norm of m times any vector is larger than h times the norm of the vector. Okay, so that's one thing. That's one auxiliary lemma. You really don't need to write it. They are in LMS, but just. Then the second one is if I have a differentiable function f, then this holds. Comes from the fundamental theorem of calculus as well. So these are things that we are going to invoke. So I'm not going to, that's your assignment, you go and think about how to prove this, but we are going to use these two results. Okay. Now let's see. So we start with, we want to show that our iterates gets closer to the solution. So that's how we start. We say x plus. So I want to see how these sort of iterations end up behaving, right? Now let's just write the relationships. So why can't I write this? Grad of fx star is equal to 0, so I can just put it there, right? So I continue. I factor h inverse. Oh, sorry. Did I put? You have to put. Do I need positive here? Probably. I need it to look like this. Sorry. Yeah. Okay. So now that's the first thing. Now I go here, write it as x minus x star plus h inverse x. Now let's look at this. Do you agree? Yeah, let's just keep it as it is. Now I want to use this is the difference between two gradients. I want to use this result. Okay? I just use it directly. I just go and say, okay, this is really now an integral between 0 to 1 of t of some Hessian x star minus x dt. Okay. All right. So now, again, these things come with experience a bit. I have these things. I want to combine everything together. Let's factor out H inverse. So this becomes here, right? I write the integral first. Well, let's do it like this. It's fine. So what should I write here? I factor out H inverse. Which would be H. Right? This is a constant in terms of t. If I look at it, it's not a function of t, right? I can move it inside this definite integral because the bounds are from 0 to 1, right? So I just do that. And then I have these two common factors. I factor them out as well. And there is a negative sign there. Because that's x minus x star. This one is x star minus x. I have to keep it like that. Like this. All good? Now this is the difference of Hessians. So I take the norm of everything. This norm is submultiplicative. So if I take the norm first, then use the submultiplicative property of the norm, it becomes this. Taking them through the integral, but this is another inequality. It's fine. Becomes h of x plus t x star minus x minus h x minus x dt. Now this, I use this. It becomes doesn't need to be positive. It would be an upper bound for it, right? Doesn't matter. I mean, I'm not saying they're equal. I'm just stacking upper bounds on top of each other. Right? One upper bound comes from the submultiplicative property of null. There's another upper bound from taking the norm inside the integral. There's another upper bound from the Lipschitz condition. So there are heaps of upper bounds there. Now I have this. What is that? Definite integral of t, 0 and 1. What is the solution?
Sorry, that's the t variable, right?
Yeah, there's a t there. Because there was a t there. Divided by 2. Right? So this is now there's no thing. All right. Okay, so for now we have this. Now let's see what we can do about that. Let's do something. Okay. Now let's do something about this term. Because it's ugly. We want to write in terms of x star, what to do. We go here and say, I just change the color because I know. Make it a bit bigger. The classic trick of adding and subtracting the same thing. I need something else. Sorry. I take some vector v, multiply it. Because I really want to use this lemma. So I take some vector v, then what I can do is this. Do I need this? Yeah. No, I'm not sure I do it in this. Sorry. The inverse comes later. So this thing becomes minus okay. Triangle inequality got the other side as well. So use that. Then this I use the Lipschitz condition again. Now from this, if I go up, I have that. I know any matrix times that will be larger than h times v, and I've already assumed this is the case. So I end up getting h v here, and then there. I factor out v. Okay, now I have this. I do have h xv larger than that. I again now move the other direction. I know now the inverse of H inverse. So the inverse of H, 1 over this coefficient. Nearly looks like magic. It's pretty good. I take this star, I plug it in here. Thus, I'll go back to my, it's less than 1 over H minus L x minus x star times x minus x star squared L2. Yeah. So this is this guy. Okay. So that was the second, as I said, second condition is the first thing we will show. But now, let's rearrange things. This is the same as saying x plus minus x star is less than. I move one of these x minus x stars in the coefficient, so it becomes L times x minus x stars, x star, without the square. H minus L right? There's a 2 somewhere there as well. Okay? Now, if I go up, I know x minus x star, the assumption was that it is in this neighborhood. Without loss of generality, let's assume beta is massive, so it is 2h over 3l is the one that dominates. Then the largest value that this coefficient can take is when I put the lower band and upper bands in it. So this thing is always less than the denominator is, sorry, how do I do this? Yeah, smart way. This guy is always less than 2h3. The numerator is always less than 2h over 3 as well. So if I really want to, in the worst case, I have to pump this term to be, takes its maximum, so it really shrinks the denominator, and takes this thing to be the maximum as well. So you really increase the numerator, so to get the biggest coefficient. I want to have a worst casey type stuff. So then it becomes, in the limit it goes to vicinity of 1, but never quite 1, because there are strict inequalities, becomes x minus x star. So this whole term, this guy becomes less than 1. All right? Now, for the other one, we go back to the original relationship that we had. Now this guy, again, this is always less than, strictly less than 2H3. I just plug it in again. Algebra, this whole thing becomes 3L over 2H. So I showed the distances are decreasing. I mean, the error is decreasing. And well, and then it's going to have this quadratic convergence rate. Here, I didn't specify the norm. It holds for any norm. So that's an interesting observation. So we might be able to show it for the neighborhoods. They don't need to be Euclidean norm, for instance. If that's your go-to norm, which is the case for a lot of people, can work for any norm, this result. That's why I like it a bit more. We didn't rely on the solution to be a minimum. We can converge to a saddle here as well. X star can be a saddle point or can be anything. Right? The only implied assumption that no one caught me on was the fact that I could factor out H inverse. But without this assumption, we cannot write the Newton method at all. So the Hessian needs to be invertible along the path as well. But that's really, I mean, if it's not invertible, we cannot write the Newton method really. Okay? I didn't finish what I wanted to finish, but it's fine. Now I'm going to quickly show you a demo of some stuff. And as I said, as I start running out of gas, our classes sometimes we finish after 2 hours, but early on I'm excited and I still can do it. Again, these notebooks are available on LMS as well. I prefer Python because I don't necessarily prefer Python. I don't like MATLAB because it makes you lazy. And then when you go and work with outside, MATLAB is expensive. Do use something that is free. Either use Python or Julia. That's my suggestion. Because the codes are readable, and you don't need to do Fortran C stuff, but you still can access the libraries. So it's nice. Anyway, it's your preference. What I want to do very quickly is look at something that we can get our head around. Let's imagine I want to minimize that function, 7 times x minus ln x. It's a scalar function. So that's what we want to minimize. So if I plot it, it ends up looking like this. So it's a nice looking function. Now let's do the Newton method. So that's the Newton iterations. And we can have a closed form formula for the Newton's iteration. It's 2 times xk minus 7x squared. You can write it down. It's not hard. Huh? Did someone say something? No? Okay. I hear stuff now. So now if you let me just do everything here. I need to write. Now let's start with some initial guesses, initial starting points. I know the solution is this because I can solve that system of equation exactly, so I don't need to worry about it. It's not really a system of equation, it's just one scalar equation. So how many starting points should we consider? Let's say 3, 4. 4 is good. I will pick 2 of the guesses, initial guesses, then you give me 2 more. So one is 0, the other one is 0.1. I need 2 more guesses. Give me numbers. 0.5? Anyone? Okay, 0.5. Something else? 5 would be ridiculous, but see. Pi? Damn it, doesn't work. You broke it. It's a mistake. What did I do? Damn it. 0. You see? 0, 0.1, 0.5 pi. That's my limit of pi. Okay. All right. This is not really showing itself. It's a terrible choices there. I have to redo it so we see something that is half meaningful. I'll keep pi there for you. No, it blows up too quickly. Okay, that's better. Now, initial condition 0, initial condition 0.1, initial condition 0.2, initial condition 0.5. Okay, we start with that. I know the solution is this, 1, 4, 2, 8, 5, 7, whatever. So, I mean, I get there with these 2 initial guesses. I get lost in the wilderness of numbers there very quickly. And I don't move. Now, something that is, I want, if anyone can point it out, they will get a cookie. Can someone point out the quadratic convergence, a telltale sign of the quadratic convergence here? Excellent. That's exactly, I will buy the cookie next. That's exactly what it is. Let's look at what happens. 1 decimal point that is correct. 2, 4, 8. Keeps going down. There is some weird thing as well. Divergence is quadratic as well. So either it works very fast or it goes crazy very fast. Look at these powers. They double. So when we talk about quadratic convergence is fast, that's what it really means. Now, if you work it out, you can work out the region of convergence of this. And this is this neighborhood. If you initialize any point here, the algorithm is going to converge. But now, just a thought experiment. Let's initialize .28, 0.29. So you have to be very careful when you work with Newton method.
How can you find the domain of a equation?
That's a very good question. What I can point you to books